On May 27, 1962, municipal sanitation workers in Centralia, Pennsylvania, initiated a routine controlled burn at the town landfill located in an abandoned strip mine pit adjacent to the Odd Fellows Cemetery. The procedure followed standard practice for the region. Ignite accumulated refuse, allow combustion to reduce volume, extinguish residual flames. Surface conditions appeared normal. The pit presented as a contained depression, suitable for waste disposal. What the workers could not observe, and what no municipal survey had verified, was that the pit floor intersected an exposed outcrop of the Buck Mountain coal seam, itself connected to miles of abandoned anthracite mine workings extending beneath the town. Within days, fire had migrated from surface refuse into the coal seam. Within weeks, it had established itself in the underground mine network. Within years, it would consume the geological foundation beneath Centralia's streets, homes, and institutions, not because anyone failed to respond, but because every response assumed the fire occupied a space it had already left. This is not a story of negligence or incompetence. It is the story of how a system designed for surface-level problems encountered a subsurface reality that invalidated every assumption embedded in standard practice. The fire did not defeat Centralia through violence. It defeated Centralia through geometry, thermodynamics, and the systematic absence of information that would have revealed the true nature of the problem before it became irreversible. The anthracite coal region of northeastern Pennsylvania developed over more than a century into one of the most extensively mined geological formations in American history. By the mid-20th century, the area beneath and surrounding Centralia contained an intricate network of abandoned mine tunnels, shafts, and voids created by decades of pillar and room extraction. This mining method removed coal in systematic chambers while leaving pillars of unmined material to support the overlying rock. When mines were abandoned, these voids remained, connected by airways, gangways, and natural fractures in the coal seam itself. The Buck Mountain seam, which outcropped at the surface in several locations around Centralia, extended laterally and vertically through this underground network, providing continuous fuel connectivity across distances measured in miles. The critical design premise that failed in Centralia was not a single engineering decision, but an accumulated institutional assumption that abandoned surface excavations could be treated as isolated, bounded containers. Strip mining operations in the region had created numerous pits where coal had been removed from surface exposures. When these pits were subsequently used for waste disposal, no regulatory framework required assessment of their connectivity to deeper mine workings. The Odd Fellows Cemetery landfill occupied one such pit. Its selection as a disposal site reflected the common assumption that a surface depression, once stripped of accessible coal, represented dead geological space with no active relationship to subsurface formations. This assumption contained a fundamental error. Strip mining removed coal from surface exposures but did not seal the interface between the stripped area and the unmined seam extending underground. The Buck Mountain seam continued from the pit floor into the subsurface, connected to abandoned deep mine workings through both direct seam continuity and through fracture networks created by decades of extraction to induced subsidence. When fire reached the exposed coal at the pit margin, it did not encounter a boundary, it encountered a pathway. The physics of underground coal combustion operate according to principles fundamentally different from surface fires. A surface fire requires continuous oxygen supply from the atmosphere and loses heat through radiation and convection to the surrounding air. Its spread is constrained by fuel discontinuity and can be interrupted by physical barriers, water application, or oxygen exclusion. An underground coal fire operates in a thermally insulated environment where heat loss is minimal. Oxygen enters through multiple diffuse pathways including fractured overburden and abandoned ventilation shafts, and fuel exists as a continuous three-dimensional mass. The fire does not spread across a surface. It propagates through a volume, following seam geometry, exploiting connectivity, and establishing multiple combustion fronts that can operate independently. The Municipal Protocol for Controlled Landfill Burns assumed a specific fire geometry, surface combustion of discrete fuel elements in an open-air environment, controllable through standard suppression techniques. This protocol contained no provisions for verifying geological isolation because the possibility of subsurface migration was not incorporated into the operational model. The workers who ignited the May 1962 burn were following procedures designed for a category of fire that ceased to exist the moment combustion reached the coal seam exposure. They did not fail to follow protocol. They followed a protocol that was categorically inapplicable to the actual conditions. The absence of subsurface connectivity data functioned as implicit confirmation of isolation. No survey had identified the seam exposure at the pit margin. No assessment had mapped the relationship between the disposal site and the underlying mine network. The information void was not recognized as a gap requiring investigation. It was processed as confirmation that no connection existed. This epistemological failure, treating absence of evidence as evidence of absence, embedded itself in every subsequent decision. When the fire persisted beyond expected duration, the initial interpretation was not that it had entered an unmapped space, but that surface suppression had been incomplete. The diagnostic framework could not accommodate a fire that had left the domain where surface diagnostics applied. The regulatory environment of 1962 contained no mechanism for preventing this category of failure. Mine safety regulations addressed active mining operations. Municipal waste management regulations addressed surface disposal practices. No regulatory domain claimed jurisdiction over the interface between abandoned mines and subsequent surface land use. Centralia occupied an institutional blind spot where the legacy of extraction-era mining intersected with mid-century municipal operations, and no authority possessed either the mandate or the information to recognize the hazard. The geological reality beneath Centralia in May 1962 was a combustion-ready environment awaiting only ignition. Miles of interconnected voids contained residual coal in pillars, floors, and unmined sections. Decades of atmospheric exposure had partially oxidized surface coal, reducing ignition temperature. Abandoned ventilation infrastructure provided oxygen pathways. Fractured overburden created additional air infiltration routes. The system was not inert. It was thermodynamically primed. The landfill burn did not create hazardous conditions. It activated conditions that had existed since the mines were abandoned. The design premise failure at Centralia was therefore not a single error, but a systematic incompatibility between surface-oriented institutional frameworks and subsurface geological reality. The fire that would eventually erase the town entered an environment where every assumption about fire behavior, spatial extent, oxygen supply, and containment feasibility was incorrect from the first moment of subsurface ignition. The workers who lit the fire, the officials who managed the response, and the engineers who designed early interventions all operated within a conceptual model that accurately described a surface fire and catastrophically misrepresented an underground coal combustion event. The conditions that transformed a routine landfill burn into an uncontrollable underground fire were not created on May 27, 1962. They accumulated over decades through the interaction of mining legacy, institutional memory loss, and operational practices that systematically excluded subsurface considerations from surface-level decision-making. By the time Centralia's sanitation workers ignited the Odd Fellows Cemetery landfill, the latent conditions for catastrophic fire migration were fully established. The human factors that shaped initial response were equally entrenched, embedded in training regimes, jurisdictional boundaries, and cognitive frameworks that could not accommodate the possibility of a fire operating outside visible, mappable space. The anthracite mining industry that created Centralia's underground void network had largely collapsed by the mid-20th century. Deep mining operations ceased as economic conditions shifted, leaving behind a physical infrastructure of tunnels, shafts, and airways that no longer served any productive function. Crucially, the institutional knowledge that accompanied active mining detailed maps of workings, understanding of ventilation patterns, awareness of seam geometry did not transfer to the municipalities that inherited the surface landscape. Mine operators possessed information about subsurface conditions that was never systematically archived, transferred to local government, or incorporated into land use planning. When mines closed, their knowledge closed with them. Centralia's municipal government in 1962 operated with no institutional memory of what lay beneath its streets. The town had been built atop and around mining operations, but by the post-war period, mining was history rather than active presence. Local officials understood that abandoned mines existed in general terms but possessed no detailed maps, no engineering assessments, and no framework for evaluating how historical extraction affected current land use. The strip pit that became the Oddfellows Cemetery landfill was selected through a process that considered surface accessibility, distance from residences, and disposal convenience. Subsurface geology was not a selection criterion because no institutional mechanism existed to make it one. The workers who conducted controlled burns at the landfill operated under protocols inherited from standard waste management practice. These protocols specified ignition procedures, monitoring requirements, and suppression methods, appropriate for surface refuse fires. Training addressed fuel types, wind conditions, and water application. It did not address geological assessment, seam identification, or subsurface fire indicators because these considerations fell outside the operational domain of municipal sanitation. The workers were competent within their defined scope. Their scope was defined by assumptions that excluded the hazard they would encounter. Fire department personnel, who would respond to reports of persistent burning, operated under similar constraints. Firefighting training and equipment in small Pennsylvania municipalities addressed structure fires, brush fires, and surface combustion events controllable through direct water application or oxygen exclusion. Underground mine fires fell outside standard firefighting doctrine, requiring specialized knowledge, equipment, and techniques that municipal departments did not possess. When early indications suggested the landfill fire had not fully extinguished, the response framework defaulted to familiar methods: additional water application, extended monitoring, repeated suppression attempts. These methods assumed a fire geometry that no longer existed. The jurisdictional landscape further complicated recognition and response. Municipal government controlled surface land use but had no authority over abandoned mine workings, which fell into a regulatory void between active mine safety oversight and municipal jurisdiction. State mining agencies retained nominal responsibility for abandoned mines but lacked resources for comprehensive monitoring and possessed no mandate to coordinate with municipal waste management operations. Federal involvement was minimal, limited to broad regulatory frameworks that did not address the specific hazard of mine fire ignition through surface activities. No single agency possessed both the authority and the information necessary to recognize the emerging disaster. The cognitive frameworks operating at every institutional level shared a common limitation: they processed information through surface-oriented categories that systematically filtered out subsurface phenomena. When residents reported unusual heat, steam, or sulfurous odors in areas away from the landfill, these reports did not immediately trigger recognition of underground fire spread. The conceptual model available to officials and residents alike did not readily accommodate fire as a phenomenon that could travel invisibly through underground channels and manifest at distant surface locations. Initial reports were often interpreted as unrelated incidents, localized phenomena, or measurement errors, rather than evidence of a connected subsurface event. Economic and political factors created additional barriers to rapid, comprehensive response. Centralia in 1962 was a declining community, its economic base eroded by the collapse of anthracite mining. Municipal resources were limited. State and federal assistance required demonstrating both the severity of the problem and jurisdictional responsibility, neither of which was clear in the early stages. The fire's invisible underground nature made severity assessment difficult. Its origin, in an unregulated interface between municipal operations and abandoned mines, made jurisdictional assignment ambiguous. These factors did not cause the fire, but they created friction that slowed recognition and delayed mobilization of resources adequate to the actual scale of the problem. The interface between human decision-makers and the physical system was mediated by indicators that reported surface conditions with reasonable accuracy, but provided no information about subsurface state. Temperature measurements at the landfill surface could confirm whether visible flames had been extinguished. They could not detect combustion proceeding through coal seams 60 feet underground. Visual inspection could identify smoke or steam emerging from known vents. It could not map the three-dimensional combustion front propagating through interconnected mine workings. The information architecture available to responders reported signals from the surface environment while the fire increasingly operated in a subsurface domain invisible to those instruments. This information asymmetry created a characteristic pattern that would repeat throughout the Centralia crisis. Surface indicators suggested the problem was localized and manageable, while the actual fire system expanded beyond any surface-based intervention capability. Decision-makers responded to the information available to them, which consistently underrepresented the true extent and trajectory of the fire. Their decisions were rational given their information. Their information was systematically incomplete in ways they had no immediate means to recognize. The human factors that shaped Centralia's trajectory were not failures of competence or diligence. They were structural features of an institutional and cognitive landscape that had never been designed to address the hazard that emerged. Training prepared workers for surface fires. Jurisdiction fragmented responsibility across agencies, none of which claimed the problem as wholly theirs. Cognitive frameworks filtered information through categories that excluded underground phenomena. Economic constraints limited resources available for response. Information systems reported surface conditions while the fire operated underground. Each factor was individually understandable, even reasonable given its context. Collectively, they created an environment where the gap between perceived conditions and actual conditions would widen progressively until the fire had established itself beyond any feasible intervention. The transformation from minor transient to uncontrollable event did not require any additional failure. It required only time for the fire to exploit the connectivity that institutional blindness had left unrecognized. Every day that passed with the fire mischaracterized as a surface problem was a day the fire used to extend through underground workings, establish new combustion fronts, and increase the energy required for any eventual suppression attempt. The latent conditions, both geological and institutional, had converted a recoverable ignition into an expanding underground combustion system before anyone possessed the information necessary to recognize what had occurred. The initiating event at Centralia was unremarkable by the standards of municipal waste management in Pennsylvania's anthracite region. On May 27, 1962, sanitation workers arrived at the Oddfellows Cemetery landfill to conduct a controlled burn of accumulated refuse. The procedure had been performed before, at this site and at similar locations throughout the region. Workers ignited the waste pile, monitored the burn, and applied water to extinguish visible flames before departing. By standard surface criteria, the operation was routine. The fire appeared controlled, then extinguished. The workers moved on to other duties. What they could not observe was that combustion had already migrated below the visible surface, entering the exposed coal seam at the pit margin and beginning its propagation into the underground mine network. The exact moment of subsurface ignition cannot be precisely determined. Fire does not announce its transition from one domain to another. What can be established is that within days of the May 27 burn, indicators began emerging that the fire had not behaved as expected. Smoke continued to rise from the landfill area despite repeated suppression efforts. Steam appeared at locations away from the original burn site. The ground in certain areas registered elevated temperatures. These observations did not immediately coalesce into a coherent picture of underground fire migration. Each indicator, taken individually, admitted alternative explanations: incomplete surface suppression, localized hotspots, unrelated thermal anomalies. The pattern that would eventually reveal subsurface propagation assembled itself gradually, and its significance was not recognized until the fire had established itself beyond easy intervention. The first divergence between system behavior and operator perception occurred in the domain of spatial extent. Surface suppression efforts assumed the fire occupied the landfill pit and its immediate surroundings. Water was applied to this area. When smoke persisted, additional water was applied. The operational model held that sufficient water application would eventually overwhelm the heat source and extinguish combustion. This model accurately describes surface fire behavior where the fire has limited thermal mass, direct atmospheric exposure, and bounded fuel supply. It does not describe underground coal fire behavior where the combustion zone is thermally insulated by surrounding rock, where water applied at the surface may not reach the actual combustion front, and where fuel supply extends continuously through seam geometry. The fire, operating according to underground combustion physics, responded to surface suppression attempts in ways that reinforced misperception. Water applied at the surface cooled the immediate area and reduced visible smoke production, creating the appearance of suppression progress. But water that penetrated to the coal seam encountered a thermal environment capable of vaporizing it before it could cool the combustion zone. Steam production actually accelerated subsurface fire spread by creating pressure differentials that drew additional oxygen into the mine workings. The intervention, designed to suppress the fire, may have contributed to its propagation, though this mechanism was not understood at the time. Within weeks of the initial ignition, residents in areas away from the landfill began reporting anomalous conditions. Steam emerged from cracks in the ground. Vegetation died in patches. Basement temperatures rose. These reports constituted the first observational evidence that the fire had migrated beyond the landfill area through underground pathways. The spatial distribution of symptoms was inconsistent with a fire confined to its ignition point. It was consistent with a fire following the Buck Mountain seam and associated mine workings beneath the town. The divergence between reality and perception widened as the fire's underground behavior became increasingly decoupled from surface indicators. At the landfill, aggressive suppression efforts appeared to bring conditions under control. Visible flames ceased, smoke production declined. Temperature readings at monitored surface points fell. By surface metrics, the situation was stabilizing. Simultaneously, the fire was establishing itself in mine workings that extended laterally and vertically from the ignition area, creating multiple combustion fronts that operated independently of conditions at the original site. The fire had not been suppressed. It had moved to locations where suppression efforts were not being applied because those locations were not yet recognized as part of the fire system. Borough officials in June 1962 hired a contractor to excavate the landfill pit and expose any remaining burning material for direct suppression. This intervention followed logical surface fire reasoning. If burning material remains below visible surface, excavate to expose it, then suppress directly. The excavation revealed burning refuse and hot coal but could not reach the combustion front that had already propagated into the mine workings beyond the pit boundary. The operation succeeded in addressing the portion of the fire that remained accessible from the surface. It could not address the fire that had entered a domain where surface excavation could not follow. By late summer 1962, the spatial extent of elevated ground temperatures and steam emergence indicated that the fire occupied a substantially larger volume than the landfill pit and its immediate surroundings. Boreholes drilled to assess subsurface conditions encountered elevated temperatures at depths and lateral distances, inconsistent with a fire confined to its ignition area. The drilling program provided the first systematic evidence that the fire had migrated through mine workings, but the full extent of propagation remained unmapped. Each borehole provided point data. The three-dimensional combustion volume had to be inferred from scattered points, an inference limited by drilling resources and complicated by the irregular geometry of abandoned mine workings. The decision fork that would define Centralia's subsequent trajectory occurred during this period, though it was not recognized as such at the time. Had the fire's subsurface extent been accurately characterized in the first weeks after ignition, intervention options existed that might have succeeded. Excavation to the coal seam, combined with flooding of connected mine workings, might have isolated the combustion zone before it established itself in the broader mine network. Injection of inert materials might have cut oxygen supply to the limited affected area. These options decreased in feasibility as the fire expanded, eventually reaching a scale where no intervention within available resources could comprehensively address the combustion volume. The temporal window for effective intervention closed without clear demarcation. There was no single moment when suppression transitioned from feasible to infeasible. The transition was continuous, driven by the fire's exponential access to fuel and oxygen through mine connectivity, while responders operated under linear assumptions about fire behavior and intervention efficacy. Each day of mischaracterization allowed the fire to expand into territory that would have to be addressed if suppression were to succeed. Each expansion increased the resources required for comprehensive intervention. By the time the fire's true extent began to be understood, the gap between available resources and required intervention had widened beyond practical closure. The initiating event at Centralia was not the landfill burn itself, but the undetected transition from surface combustion to underground propagation. The divergence from perceived to actual conditions began in that transition and widened with every subsequent intervention designed for a surface fire applied to an underground combustion system. The fire that would eventually displace Centralia's population was fully established in its subsurface domain before anyone possessed the information necessary to recognize that a fundamentally different category of event had occurred. The physics of underground coal combustion operate according to principles that diverge fundamentally from surface fire behavior, and it was this divergence that transformed Centralia's landfill fire into an uncontrollable geological event. Once combustion established itself in the Buck Mountain seam and connected mine workings, the fire entered a thermodynamic regime where conventional suppression logic not only failed, but in some cases accelerated the processes it was designed to interrupt. Understanding the failure chain at Centralia requires examining how coal burns underground, how abandoned mines provide the conditions for sustained combustion, and how each intervention attempt interacted with a physical system operating outside the boundaries of surface fire assumptions. Coal combustion requires three elements: fuel, oxygen, and sufficient temperature to initiate and sustain the oxidation reaction. On the surface, fire consumes available fuel, draws oxygen from the surrounding atmosphere, and loses heat through radiation and convection to the environment. These characteristics make surface fires self-limiting in important ways. Fuel depletion eventually starves the reaction. Heat loss prevents indefinite temperature escalation. Oxygen supply, while abundant, arrives through predictable atmospheric pathways that can be interrupted through physical barriers or smothering agents. Underground coal combustion operates under different constraints. The fuel is not discrete material that can be consumed and exhausted, but a continuous geological formation extending through three-dimensional space. Heat loss is minimal because the combustion zone is surrounded by rock that acts as thermal insulation, retaining energy that would dissipate in an open-air fire. Oxygen supply arrives through multiple diffuse pathways, including fractured overburden, abandoned ventilation shafts, boreholes, and natural permeability in the rock mass. The Buck Mountain seam beneath Centralia provided an effectively unlimited fuel supply for any combustion front that established itself in the coal. The seam thickness, continuity, and lateral extent meant that fire could propagate indefinitely as long as oxygen supply and temperature conditions permitted. Unlike a surface fuel pile that can be exhausted, the coal seam regenerated fuel availability simply by burning through to adjacent unmined sections. The fire did not need to be fed, it needed only to move through a geological formation that constituted, from a combustion perspective, a continuous fuel matrix. Oxygen supply to the underground fire derived from the abandoned mine infrastructure that 19th and early 20th century extraction had created. Pillar and room mining left interconnected void spaces that functioned as airways, allowing atmospheric oxygen to penetrate deep into the subsurface. Abandoned ventilation shafts, some sealed and some open, provided vertical conduits between atmosphere and mine workings. Natural fracturing in the overburden, exacerbated by decades of subsidence as mine pillars deteriorated, created additional permeability pathways. The fire drew oxygen through this distributed network, establishing airflow patterns driven by temperature differentials between hot combustion zones and cooler surrounding rock. Hot air rising from the fire created negative pressure that drew fresh atmospheric air into the mine system through available pathways, sustaining combustion without any external oxygen supply intervention. The thermal regime underground differed qualitatively from surface conditions. Rock surrounding the combustion zone absorbed heat from the burning coal, but conducted that heat away slowly, creating a thermal reservoir that maintained combustion temperatures even during periods of reduced oxygen supply. Surface fires that are smothered or deprived of oxygen typically extinguish as their fuel cools below ignition temperature. Underground coal fires can enter a smoldering state during oxygen-limited periods, maintaining temperatures sufficient to reignite when oxygen supply resumes. This thermal resilience made the Centralia fire resistant to suppression strategies based on temporary oxygen exclusion. Sealing ventilation pathways might reduce oxygen flow, but the fire could persist in reduced combustion or smoldering modes until new oxygen pathways developed through overburden fracturing or seal deterioration. Water application. The default surface fire suppression technique encountered fundamental limitations underground. Water poured on the surface had to percolate through fractured rock to reach the actual combustion zone, often tens or hundreds of feet below. Much of the applied water never reached the fire, instead flowing through the rock mass along pathways determined by local permeability and fracture geometry. Water that did reach the combustion zone encountered temperatures sufficient to flash it immediately to steam, absorbing latent heat but creating pressure pulses that could actually enhance oxygen infiltration through surrounding fractures. The steam itself, at high temperatures, could participate in chemical reactions with hot coal that produced combustible gases, adding complexity to the already uncontrollable combustion chemistry. The failure chain at Centralia followed a characteristic pattern of intervention-response expansion. Each major suppression attempt addressed the fire as it was understood at the time of the attempt, which systematically underestimated actual extent. The fire, operating in 3 dimensions through mine connectivity, expanded to occupy volumes beyond the intervention scope while the intervention was being implemented. By the time one phase of suppression was assessed and found inadequate, the fire had migrated to territory that would require an entirely new intervention design. This pattern repeated through multiple suppression projects spanning years, with each project targeting a fire perimeter that the fire had already exceeded. Flushing operations, which involved pumping water and incombustible slurry into mine workings to flood the combustion zone, founded on the problem of 3-dimensional geometry. The abandoned mine network was not a single cavity that could be filled like a container. It was an irregular, interconnected maze of tunnels, rooms, and collapsed areas with uncertain connectivity. Slurry pumped into one section might flow through connected passages away from the combustion zone, filling void space that was not burning while leaving the active fire unaddressed. Without accurate maps of mine geometry, maps that largely did not exist or had been lost when mining operations ceased, flushing operations could not reliably target the actual combustion volume. Excavation projects, which sought to physically remove burning coal and break the continuity of the fuel supply, confronted the depth and extent of the fire. Trenching to the coal seam could create barriers to fire spread if the trench fully severed seam continuity and was maintained against collapse and erosion. But the depth to the seam in many areas exceeded practical excavation limits, and the lateral extent of the fire by the time major excavation projects were considered required trenching on a scale measured in miles, not hundreds of feet. Cost estimates for comprehensive excavation ranged into hundreds of millions of dollars, figures that could not be justified for a community of Centralia's size and economic circumstances. The physical processes driving the fire's expansion created a temporal dynamic that worked systematically against intervention success. The combustion front advanced through the coal seam at rates determined by local oxygen supply, coal permeability, and seam geometry. During periods of active intervention, front advance might slow or locally pause. During periods between interventions, when funding was being secured or new approaches were being designed, the front continued its propagation. The cumulative effect was ratchet-like. The fire's extent increased during intervention gaps faster than it could be reduced during active suppression, creating a net expansion trend that no intervention sequence successfully reversed. By the mid-1960s, borehole temperature surveys and surface subsidence patterns indicated that the fire occupied a substantial volume of the mine workings beneath the eastern portion of Centralia. The combustion zone was no longer a single front, but a complex three-dimensional region with multiple active areas connected through mine passages and seam continuity. The fire had achieved a configuration that no feasible intervention could comprehensively address. It had not defeated suppression efforts through any single mechanism. It had exploited the mismatch between three-dimensional underground expansion and two-dimensional surface intervention logic until the gap between fire extent and intervention capacity became unbridgeable. The period from the mid-1960s through the early 1980s was characterized by repeated stabilization attempts, each designed to address the fire as understood at the time of project initiation, and each ultimately unsuccessful in reversing or containing the fire's expansion. These attempts were not irrational. They represented systematic applications of available engineering knowledge to a problem that fell outside standard categories. But each project operated under constraints that limited its effectiveness: incomplete information about fire extent and mine geometry, funding levels inadequate to comprehensive intervention, and time lags between project conception and implementation, during which the fire continued to expand. The stabilization era at Centralia demonstrates how secondary crises emerge not from inaction but from the interaction between partial interventions and a physical system that exploits the gaps between them. The first major federally funded project began in 1967, when the Bureau of Mines initiated an attempt to isolate the fire through a combination of flushing and barrier construction. The project design assumed that the fire occupied a mappable volume bounded by identifiable geological and structural features. Workers drilled boreholes to inject incombustible material into mine voids, seeking to create barriers that would cut oxygen supply to the combustion zone. Simultaneously, trenching operations sought to sever the coal seam at the fire's presumed perimeter, interrupting fuel continuity. The project proceeded through 1969, expending approximately $500,000 in federal and state funds. The 1967 to 1969 project failed because its underlying spatial model was incorrect. The fire had not remained within the boundaries assumed by the project design. While flushing and trenching operations addressed the presumed perimeter, The actual combustion front had already propagated beyond that perimeter through mine passages and seam continuity. Boreholes drilled to assess project effectiveness revealed elevated temperatures in areas outside the project's scope. The barriers constructed did not enclose the fire because the fire had already escaped the enclosed area. The project succeeded in filling certain mine voids with incombustible material and in severing the seam along certain lines. It did not succeed in isolating or suppressing the fire, which continued to expand through pathways that the project had not addressed. A second major project, in 1969 to 1972, attempted to learn from the first project's limitations by expanding the intervention scope. Additional boreholes were drilled to map the fire's extent more comprehensively. Flushing operations targeted a larger volume. Excavation efforts sought to reach the coal seam at greater depths. Total expenditures exceeded $3 million. The project achieved localized temperature reductions in some areas and may have slowed the fire's advance in certain directions. It did not achieve containment. Post-project monitoring indicated that the fire continued to propagate through areas that had been inaccessible to the intervention or that had been incorrectly assessed as uninvolved. The pattern that emerged from these early stabilization attempts revealed a fundamental mismatch between project timelines and fire dynamics. Engineering projects operate according to sequential phases: assessment, design, funding, implementation, evaluation. Each phase requires time. The Centralia fire operated continuously, expanding through mine workings without regard to human planning cycles. A project designed to address fire extent at time t would be implemented at time t plus 2 years, by which point fire extent had increased. The project would address the fire's past configuration while the fire occupied a new, larger configuration. This temporal mismatch was not a design flaw that could be corrected through better planning. It was a structural feature of attempting to address a continuously expanding phenomenon through discrete, sequentially funded projects. Funding limitations compounded the temporal mismatch. Comprehensive intervention, capable of addressing the fire's full three-dimensional extent, would have required resource mobilization on a scale that could not be justified for a community of fewer than 2,000 residents. Each project was therefore scoped to available funding rather than to intervention requirements. The projects were large enough to create expectations of success and to consume available budgets, but not large enough to actually encompass the fire's extent. This created a secondary crisis dynamic. Each unsuccessful project consumed resources that then had to be regenerated through new funding cycles before subsequent attempts could proceed, extending the time gaps during which the fire expanded unopposed. The human dimensions of the stabilization era imposed their own constraints. Centralia's residents lived atop an ongoing underground fire, exposed to periodic intrusions of carbon monoxide, steam, and subsidence hazards. Health impacts, though difficult to attribute definitively to fire exposure, accumulated through respiratory symptoms, anxiety, and the chronic stress of uncertain safety. Property values declined as the fire's persistence became recognized. Residents faced a choice between remaining in homes of diminishing value and safety or relocating at personal financial loss. This human crisis demanded response independent of technical fire suppression considerations, creating political pressure to demonstrate action even when technically effective action was not achievable. State and federal agencies responded to this pressure through buyout programs that allowed residents to sell their properties to the government and relocate. The first systematic buyout began in 1984 following congressional appropriation of funds for voluntary acquisition. The buyout addressed the human crisis by removing people from hazard exposure, but did nothing to address the fire itself. In some respects, the buyout may have reduced pressure for continued fire suppression investment by removing the population whose presence had justified intervention funding. Once residents were relocated, The argument for expensive fire suppression weakened. The fire could be left to burn through a depopulated landscape where it endangered no one. Secondary crises emerged from the intersection of stabilization attempts and continuing fire behavior. Subsidence events, caused by the collapse of fire-weakened mine pillars and coal pillars consumed by combustion, created surface hazards, including sinkholes and ground settlement. A particularly dramatic subsidence incident in 1981 nearly claimed the life of a 12-year-old resident when a sinkhole opened beneath him in his grandmother's backyard, exposing him to hot gases and requiring rescue. This incident crystallized public attention on the ongoing hazard and contributed to the political momentum for the 1984 buyout program. The subsidence was not an independent phenomenon, but a direct physical consequence of the underground fire-consuming coal that had previously provided structural support for overlying rock. Carbon monoxide intrusion into buildings constituted another secondary crisis. The fire produced carbon monoxide as an incomplete combustion product, and this gas migrated through fractured rock and mine passages to infiltrate basements and ground floor spaces. Monitoring programs detected elevated carbon monoxide levels in multiple buildings, requiring ventilation interventions and, in some cases, evacuation. The carbon monoxide hazard was invisible and could accumulate to dangerous levels without obvious warning, creating a chronic health risk that monitoring programs could identify but not eliminate. Steam and hot gas emissions at the surface created localized hazards and rendered certain areas unusable. Roads developed hotspots where subsurface fire heated the ground to temperatures that damaged pavement and posed contact hazards. Vegetation died in zones where soil temperatures exceeded tolerance limits. The surface landscape of Centralia progressively displayed the fire's subsurface presence through these thermal manifestations, transforming familiar terrain into a visible record of underground combustion. By the mid-1980s, the stabilization era had effectively concluded without achieving stabilization. The fire continued to burn. The technical community had not developed an intervention capable of suppressing or containing it within available resources. The human community had largely relocated, their former homes demolished to prevent vandalism and remove liability exposure. Centralia transitioned from an engineering problem to be solved into a geological phenomenon to be monitored. The fire had not been defeated by any specific failure. It had persisted through a sequence of partial interventions, each inadequate to the full scope of the problem, until the problem outlasted the community it threatened. 8:34 p.m. The forensic evidence that accumulated over decades of monitoring, intervention, and observation ultimately confirmed what early indicators had suggested, but institutional frameworks had been unable to process. The Centralia fire was not a discrete event amenable to suppression, but a geological phenomenon operating according to physical principles that rendered standard intervention approaches ineffective. Post hoc analysis revealed the mechanisms that had driven the fire's persistence and expansion, validated certain early concerns that had been dismissed or underweighted, and identified systemic failures in the institutional frameworks that governed the interface between abandoned mining infrastructure and post-mining land use. The lessons of Centralia extend beyond a single Pennsylvania town to illuminate fundamental problems in how societies manage legacy industrial landscapes and the hazards they contain. Temperature monitoring conducted over decades mapped the fire's progression through the mine workings, beneath and beyond Centralia. Borehole surveys established that the combustion zone expanded from its initial ignition area to encompass a substantial volume of the Buck Mountain seam and connected workings. By the 1980s, the fire extended over an area measured in hundreds of acres, with active combustion fronts advancing through the seam at rates estimated between 50 and 75 feet per year in some directions. Projections based on these advance rates and known seam geometry suggested the fire could continue burning for decades or centuries, limited only by the eventual exhaustion of accessible coal or the intervention of geological barriers that the seam did not cross. Surface manifestations documented the fire's subsurface behavior through observable physical evidence. Subsidence mapping recorded the collapse of surface areas where underground combustion had consumed coal pillars and destabilized mine roofs. Thermal imagery identified hotspots where elevated subsurface temperatures conducted to the surface, creating patterns that traced the underground combustion geometry. Vegetation surveys documented kill zones where soil temperatures exceeded plant tolerance, leaving barren patches that marked the fire's passage beneath. Gas monitoring recorded carbon monoxide, carbon dioxide, sulfur compounds, and other combustion products emerging through cracks, boreholes, and subsidence features. Collectively, these surface observations provided a proxy record of underground conditions, allowing researchers to track fire behavior without direct subsurface access. Chemical analysis of emitted gases confirmed the combustion processes operating underground. The gas composition reflected incomplete combustion characteristic of oxygen-limited burning, with elevated carbon monoxide ratios indicating that the fire persisted in smoldering or reduced oxygen modes across much of its extent, punctuated by regions of more complete combustion where oxygen supply was more abundant. Sulfur compound emissions derived from pyrite and other sulfur-bearing minerals in the coal and surrounding rock, contributing to the characteristic odors reported by residents before relocation. The gas chemistry demonstrated that the fire operated as a complex chemical system, not a simple combustion process, with multiple reaction pathways determined by local oxygen availability, temperature, and mineral content. Geological surveys conducted to support intervention planning and post-event analysis revealed the mine network geometry that had enabled fire propagation. Historical mining records, where they could be located, documented the extent of 19th and early 20th century extraction, but often lacked the precision necessary for intervention planning. Mine maps that existed frequently contained errors, omissions, or ambiguities reflecting the documentation practices of their era. Exploratory drilling to supplement historical records encountered the irregular reality of abandoned workings. Some areas matched historical maps, others did not, and many regions had no historical documentation at all. The geological complexity underlying Centralia exceeded what any intervention planning process had adequately characterized, contributing to the spatial mismatches that plagued suppression attempts. The institutional failures illuminated by Centralia extended beyond any single agency or decision. The fundamental failure was categorical. No framework existed for managing the hazard that emerged. Mine safety regulation addressed active mining operations and assumed that abandoned mines entered a static, stable condition, requiring no ongoing management. Municipal land use regulation addressed surface activities and assumed that subsurface conditions were either irrelevant or stable. The interface between these domains, where surface activities could interact with abandoned subsurface workings in hazardous ways, fell outside both regulatory frameworks. Centralia demonstrated the consequences of this regulatory gap. A routine municipal activity initiated a catastrophic process because no institutional mechanism required assessment of subsurface risk before surface operations proceeded. The information failures at Centralia were equally systemic. Knowledge of mine geometry, seam location, and connectivity had existed during active mining but was not systematically preserved or transferred when mining ceased. The institutional memory of underground conditions evaporated with the mining companies that had created those conditions. Municipal governments inherited surface landscapes without inheriting the subsurface knowledge necessary to manage them safely. When the fire began, responders had to reconstruct underground information from fragmentary historical records, exploratory drilling, and inference from surface manifestations. This information reconstruction occurred under time pressure while the fire expanded, ensuring that understanding consistently lagged behind fire extent. The temporal dimension of Centralia's failure reflected a mismatch between geological and institutional timescales. The fire operated continuously, propagating through the seam without interruption for funding cycles, planning processes, or political transitions. Institutional response operated discontinuously, organized around project phases, budget years, and administrative procedures. The fire's continuous advance against discontinuous response created the ratchet dynamic observed throughout the event. Fire extent increased between interventions faster than it could be reduced during interventions. This temporal mismatch was not a correctable error, but a structural feature of how human institutions engage with ongoing geological processes. Centralia's legacy in regulatory and institutional practice emerged gradually from the recognition that similar hazards existed throughout coal mining regions. Abandoned mine land programs, administered at state and federal levels, incorporated lessons from Centralia into site assessment and reclamation protocols, requirements for subsurface evaluation before surface disturbance in mining-affected areas, addressed the categorical gap that had allowed Centralia's fire to ignite unrecognized. Mine fire monitoring and response capabilities developed in response to Centralia and similar events, creating institutional capacity that had not existed in 1962. These developments did not prevent the Centralia fire or restore the town it consumed, but they represented systemic learning that could reduce the probability of similar failures elsewhere. The town of Centralia itself persisted as a geographic location while ceasing to exist as a community. By 2020, fewer than 10 residents remained, their properties scattered among demolished lots and abandoned streets. The fire continued to burn beneath the surface, monitored but not suppressed. State highway routes that once passed through Centralia were relocated to avoid subsidence hazards. The town's streets remained, cracked and heated in places, visited by tourists curious about the underground fire and by researchers monitoring its continued progression. Centralia became a landscape of absence, its former community preserved only in historical records and the memories of displaced residents. The final lesson of Centralia concerns the limits of intervention against certain categories of physical processes. Once the fire established itself in the underground mine network, no intervention within practical resource constraints could comprehensively address the combustion volume. The fire did not defeat human intervention through any exceptional mechanism. It simply occupied a physical domain where intervention was geometrically impractical, thermodynamically unfavorable, and economically unjustifiable. The failure at Centralia was not a failure to try, but a failure to recognize, early enough to matter, that the category of problem had changed from recoverable surface event to uncontrollable subsurface process. That recognition failure was not individual but institutional, embedded in frameworks that could not see what they were not designed to see. The fire burned according to physics. The institutions responded according to their design. The mismatch between these two systems determined the outcome before anyone understood that the outcome had already been determined. The contradiction at Centralia's core was precisely this: the fire did not overwhelm response capacity through scale or violence. It escaped response capacity by entering a domain where response frameworks did not apply. Every indicator that responders monitored reported accurately. Every procedure they followed was executed correctly. Every decision they made was rational given available information, and the fire burned on, beneath a town that slowly emptied, through a seam that stretched for miles, following physics that no surface-oriented framework could reach. Centralia was not lost to negligence or incompetence. It was lost to the systematic absence of institutions capable of perceiving and responding to the hazard that actually existed. The information structure made the wrong responses plausible. The geological structure made those responses ineffective. Between the two structures, a town disappeared.